So yeah, first of all, yeah, it's really nice to be here. This is my first in-person talk in, I think, 3 years. So well, I think I gave one at Warwick actually, but it's definitely my first external talk for the first time in a long time. So it's really nice to be here. And thanks to Xiaocheng for inviting me. So I'm going to talk today about coarse-graining of stochastic dynamics via the Mori-Zwanzig formalism, as the title says. So I know that the audience of this seminar is pretty broad, so I will try to motivate. There's a lot of technical words in my title, but I'll try to motivate what the problem is from a fairly applied perspective to start with. So, in many areas of applied maths, there's lots that we have high dimensional dynamical systems that we're interested in. So that could be, for example, a discretization of some PDE. You know, when you have a mesh for some PDE that covers some evolution equation, then you have a very high dimensional system that you need to solve, propagate forward in time. From my own perspective, I mean, the thing that I'm interested in through a lot of my research is in models of materials, mathematical models of materials. And so my motivation for thinking about this particular topic is from molecular dynamics. So this is a simulation technique where you have many degrees of freedom describing the individual nuclei in a particular material, and you propagate this forward in time using a Hamiltonian dynamics, or maybe some variant thereof, which I'll talk about more in a second. And then you actually want to extract various physical predictions from both your PDEs and your molecular dynamics simulation. So there's typically some output that you want to actually compute using this complicated high-dimensional system of equations. So I've given some examples here. So for example, in MD, very often you might want to compute a diffusion coefficient of some molecule through some solvent. That's a typical example. So this is really just one number that comes out of a very high-dimensional dynamical system. Or if you're interested in some fluid dynamics problem where you're interested about diffusion and transport of some a solvent in a fluid, you might be interested in the boundary flux at the outflow over time, for example. So this is really, again, one number that you get out of a very complicated system of equations that you're simulating. And so that really motivates the idea that often we want to simplify high-dimensional complicated dynamical systems and get some kind of proxy model that really describes just how this one number, how a complicated initial condition propagates through to get one number out, right? So this is a really current problem. People are thinking about this a lot, right? That's the whole point of lots of machine learning strategies, is to try and get predictions out of this type. So here I'm going to give you a little bit more background on molecular dynamics first of all. So what is molecular dynamics? So it's really, so it's basically Hamiltonian dynamics. So we have both positions and momenta of basically atoms or nuclei treated as essentially small classical particles. And so they have the momentum part of molecular dynamics is fairly straightforward. We give each of these particles some mass, which is the atomic weight of the particular nucleus that we're concerned with. We give it a velocity and we give it a momentum. That's fairly straightforward. The complicated part is describing the interaction energy between the particular nuclei in the molecule that we're interested in. And so typically there, people write down very complicated high-dimensional potential energies which are fitted to experiment and have very large numbers of parameters. And there's a whole story about trying to describe such potential energies in detail, which is a story that I won't be talking about here. But what I'm going to assume is that essentially we have one of these potential energies, V, that describes a very large, the potential energy of a very large number of atomic nuclei based on their positions, Qi. And then the problem of molecular dynamics is really a problem of statistical mechanics. So we have some total energy of the system, which is basically kinetic energy plus potential energy. So that's kind of your Hamiltonian. And then typically what you seek to sample is one of these measures, which are called the microcanonical or the canonical ensemble. So the microcanonical ensemble basically says, assume that I know the energy of the system. What are all the states? What are all the positions and momenta of the system which are consistent with that observation? And for the canonical ensemble, it's the same idea. It's just that I fix the temperature instead of the total energy. And the canonical ensemble is the sort of the most common ensemble that people are interested in. So you assume there's some equilibrium at fixed temperature, and then you care about the properties of your system at that temperature. So this is, I've written down some equation for a measure here. The thing that you just need to take away from that is there's a very nasty, complicated measure that I care about, and actually all I care about is some single number that I can extract from that measure in practice, and that's what you would like to be able to detect using whatever simulation technique you have, and use as little computational resource to do that as possible. So how do people do this in practice? So they use a dynamical system, as I said. So the two kind of prototypical examples that explore these ensembles that I've written down here. So these measures are either the kind of classical Hamiltonian dynamics, which you may have seen in a classical mechanics course. And then there's a kind of equivalent thermostated Hamiltonian dynamics. So you take the Hamiltonian dynamics, which is still here in black, and you add on this thing that is a thermostat, which is basically a stochastic process to your Hamiltonian dynamics, and this will explore the canonical ensemble rather than the microcanonical ensemble. So the point here is Hamiltonian dynamics preserves energy, and so that's why it preserves the microcanonical ensemble. The story about the Langevin dynamics is a bit more complicated, but essentially this will still be ergodic with respect to the canonical ensemble, if that means anything to you. Yeah. And so what we're typically interested in is some observable, which is a function, which again might just be one number really that comes out of all of these positions and momenta in the system. And for typical molecular dynamics applications, you want the number of particles to be as large as possible, effectively. So if you're considering like diffusion of some solvent, of some compound in a solvent, you really would like to like track as many of these particles for as long as possible. So you want to really maximize, you know, the price of your computational. You basically want to use all of your computational resource that you have, because that's typically how you get the best predictions. So this means that you're definitely doing thousands, if not tens of thousands, if not millions of atoms. So therefore, possibly tens of millions of degrees of freedom, because there's 3 spatial and momentum, 6 total degrees of freedom for each atom in your simulation. So this can be very large and takes a very large amount of computer time. So I'm sure that Birmingham has a supercomputer, and I'm sure that a very large percentage of its time is spent doing these things if you have people that do MD here. So once you have, so one way to think about what happens if we, so we take this dynamics, which is what we believe the dynamics of all the degrees of freedom in our system to be, we can then ask, well, what's the dynamics of the observable that's determined in terms of those degrees of freedom? And so in both Hamiltonian mechanics and also this Langevin particle dynamics, there's equations that we can write down for these things that determine basically how the observables evolve in time. And so in principle, we have an equation that tells us how to describe the evolution of these observables. But what you might notice in here is that, so in particular, the easiest way to see this here is the P. This thing requires me to know the evolution of P in order to predict the evolution of F. So if I just take this, I still need to know like the full evolution of all of the individual particles to actually make a prediction about the evolution of the observable, which is not really that surprising. But what we're going to talk about is basically how to try to formulate and close models which try to avoid using all of the complicated dynamics, and think about that. And that's going to be what coarse-graining is, effectively. So maybe one final slide on just talking about coarse-graining in general. So another reason that people use coarse-graining rather than really focusing on just one observable is actually to just reduce the number of degrees of freedom in your system. That's actually a much more common use of the form of coarse-graining I'm going to talk about here. So if you imagine like a very long chain polymer, then in polymers, you typically have lots of repeating units. And if you have repeating units, well, then you kind of hope that perhaps the same units interacting with each other might have similar dynamics. And so then if polymers can have, thousands and thousands of isomers involved in them. So then I'd much prefer to reduce the system to maybe having 1,000 degrees of freedom rather than 10,000 degrees of freedom. And so people try to formulate kind of beads made up of lots of these atoms in units interacting, and that's another way that you can use coarse-grained molecular dynamics. And that's really the point here, is that the computational bottleneck for any molecular dynamics simulation is really evaluating the forces in your model, because that tends to be the hardest thing to evaluate. I need to evaluate the gradient of this potential energy, or just more generally, the force field, which is the most costly thing to do in each time step of a molecular dynamics simulation. And so a more naive thing is just literally to kind of make a simpler dynamical system that still has all of the same properties that the large high dimensional dynamical system has. So yeah, that's probably all I wanted to say there. So yeah, I think I've said most of this already. The point is that we have a very high dimensional dynamical system. We care only about limited amounts of information taken from the whole dynamical system. We'd like it as quickly as possible and as accurately as possible. Of course, you can't have all of these things. There's no free lunch, but we need to, if we want to put down some reduced models, we want to have some confidence about how accurate they are. And so that's what we're going to talk about. How can we discard information in a controlled way, ideally? Okay, so there's been a lot of work, as I was saying. I mean, firstly, there's lots of work on machine learning more recently applied to this kind of idea, but there's been a lot of work over a long period of time on all kinds of coarse graining, because this is a very relevant thing, as I've said, for all kinds of applications. And I've listed a few particular techniques that people have thought about here. There's lots and lots of them. In short, lots of people have thought about kind of reduction of dynamical systems and how to do this and make predictions and do uncertainty quantification. So understand how uncertainties are going to propagate through to reduce systems and so forth. So I learned about some of this stuff when I was a postdoc in Paris. I know that Xiaocheng knows the guys in Paris that I worked with. So Tony Lelièvre and Frédéric Le Gall have done some stuff on this related to what they would call reaction coordinates. So that's where you're really concerned with maybe just one angle in some molecule, which is relevant for protein folding or something like that, or maybe a couple of angles and this kind of thing. So lots of the techniques that have been looked at so far, particularly, so some of this work is related to sampling. So I said that there's these measures, and what we want to do is maybe to evolve our dynamics and sample from these measures. Lots of the techniques have been developed to overcome what are called energetic barriers. So that means typically we've got something where the system is we have this very complicated potential energy V. It has lots of local minima. And what can happen is that the system likes to stay in a local minimum and takes a while to escape because it needs to basically climb out of the little valley that it's got itself stuck in. so over here. And in order to do that, it basically has to climb over a kind of saddle, much like if you're mountain climbing and you're in one valley, you need to go over a saddle effectively between mountains in order to go into some other valley. But not so much has been done to think about the kind of entropic, what are called entropic barriers. So energetic barriers means that there's some kind of difficult, I have to go up in energy in order to get into a new local minimum. But for an entropic barrier, typically there's no real energetic barrier, but the pathway to actually get from one state to another could be very narrow. And so what we were interested in this work was to think about kind of the balance between these two different things, and not so much seems to have been thought about in terms of the entropic barriers. I mean, people know it's a problem, but there's not really much knowledge of how to deal with this in practice. And obviously in high dimensional systems, actually entropic barriers are as much of a problem as energetic barriers are. Yeah.
Is there anything to do with entropy of the system, like Boltzmann entropy?
So yes, effectively, so the story is quite long, but I mean, in some sense, you can think of, so let's say this first one is a case where you can do transition state theory and you're okay. Over here, you don't really, classical transition state theory is not going to deal with this because it's kind of, the barrier is low relative to the temperature, but what happens is the pathway is thin. And so it's, I mean, you can do various things to turn this into a kind of new entropic. You can turn this into an energy barrier in terms of a free energy, but maybe not an energy barrier in terms of the original potential energy, let's say. I don't know if that, we can talk more about this afterwards if you want.
Z there is a B, right?
Yeah. So yeah, this Z here, this is taken from this paper, but this Z is just an example of V, or a couple of examples of V. So here, yeah, we have a V that has really a proper saddle point, and over here we have a V that also has a saddle point, but the more important thing is that this gap is much narrower than this gap, and so that's why it's entropic, because you know, you need actually additional entropic information. So in the prefactor in your transition theory, you need that information that you can't easily get hold of directly necessarily. So yeah, a few years ago, so this is joint work, I should have said this at the start, with my collaborator Xingjie Li, who's based in Charlotte. And Helen came to me a few years back now and said, oh, we should think about this a little bit together. And, you know, I mean, in retrospect, we can write down our goals, but of course, that's not exactly how this project went in the first place. But I guess what we decided was we'd like to understand a little bit more about how coarse graining works, and when ultimately we'd like to know is when can we actually coarse grain effectively and reliably. That would be the kind of ultimate goal of what we want to do. But in practice, of course, you don't attract such lofty goals straight off. So we decided what we would like to do is try to think about how coarse graining interacts with a form of dynamics, which is kind of a more basic form of the dynamics I showed you before. So that's going to be the overdamped Langevin dynamics. So this is really like a gradient flow plus the stochastic perturbation, and think about that. And so what we decided to use was this thing called the Mori-Zwanzig formalism, which I'll explain to you in a minute, and to think about the, as we'll see, that allows us to think a little bit about the error that we commit when we try to reduce a system to some kind of closed form in terms of a particular coarse grain variable that we're interested in. And yeah, so I'll talk about that in more detail. And so, yes, we're not doing the full dynamics that I showed you before, but we're doing something that's very common. It's got much nicer mathematical structure as a first step, with the aim of trying to understand as much as possible and then try to use the lessons we learned to attack maybe the more complicated full dynamics, which people really care about for MD in practice. So the Langevin, overdamped Langevin dynamics we're going to consider is this. So like I said, it's not like this kind of Hamiltonian structure. It's really just a gradient flow plus some perturbation, which it's going to be as simple as possible. It's really just going to be some Brownian noise with some particular variance. This is still, so this is kind of analogous with the full Langevin dynamics in that it's ergodic with respect to a particular measure that's closely related to the Boltzmann-Gibbs measure I showed you before. So it's this measure at fixed temperature. So it's still a thermostatic dynamics. It's just that it doesn't have a momentum involved. It just has positions, x now. And so just as we had before, we can define using Ito calculus what happens to a linear observable G, which is just a linear function of our full selection of variables x, and we can work out what the law of we can work out what the SDE that this linear observable satisfies is, and it takes this form. So you'll see here that there is basically it's still not a closed equation because I would like ideally to have, if I think of G as the observable that I care about, what I would like is an equation for G that depends only on G and possibly a Brownian noise. And here I have a G that's being propagated in terms of some Brownian noise, great. But here I still need the full forces projected according to this this phi thing in order to actually work out how G moves forward in time. So effectively, I've written down an equation that determines how G varies in time, but it's not a closed equation for G in terms of itself. So what can I do to resolve that? Well, what I can do is to apply the Mori-Zwanzig formalism. So at a very high level, the Mori-Zwanzig formalism is basically just kind of variation of constants. It's nothing super complicated. And I'll explain how this relates, because I've started with a very non-linear dynamical system here. Right, in general, this phi could be very complicated, as I've said. And now I'm going to talk about linear dynamical systems, but I'll link that back together in a little bit. So the idea of the Mori-Zwanzig formalism is really just to think about a linear system. So if you prefer, just think of really as this particular equation and think of L as a matrix. So really think of everything in finite dimensions. So F is a vector, L is a matrix. So then from your kind of differential equations that you probably did as an undergrad, you know that you can write down the solution of this linear equation basically using this matrix exponential. So if L is some operator or some matrix, then we can just write this down. And now what we're going to do is we're going to give ourselves two orthogonal projections P and Q. Again, you can think of these as just matrices. We're going to assume that these add together to give the identity. So in general, what we're going to assume is that we've got a P and we can just define Q as I, the identity minus P. And so then if I want to, basically I can manipulate the equation, the matrix exponential here in this nice way. So if I take derivatives in time, then this brings out a copy of the operator L. And then I can basically treat the identity that's hiding in between e to the t L and L and split this as P plus Q. And then I can do this. And then what I am going to do is basically use the Dyson-Duhamel principle or the variation of constants to write e to the t L in this last term as the sum of these two things. So this is the slightly more complicated step that you might need to sit down and work through for yourself. But essentially, you can use this integral formulation to actually kind of work out how to rewrite this e to the TL in this particular form. And so then if I put this together, so I've basically got this. I'm going to leave this term as it is. That's what this term remains here. I've got a QL here, which I'm going to post-multiply by these two terms to get what I have here, these two additional terms. So that you might wonder, why on earth am I doing all of these things? And it's not completely clear, and took us a very long time to work out exactly why you would want to do these things. But the idea that Mori-Zwanzig kind of had in the 60s is to treat these things as kind of error terms. And we can think of these things, so physicists tend to think of these things as fluctuation and dissipation. So this QL is basically kind of so if we think of PL as giving us a projection onto the variables we care about, so P projects onto the variables we care about, then this is kind of QL is all the fluctuations in the variables that we don't know anything about if we want to reduce the system. And so this e to the TQL times QL is basically describing how all of these variables we would like to forget about are going to self-interact. And so that's kind of gives it fluctuations. This complicated integral term, which I've noticed there's an extra e to the t times s, which shouldn't, t minus s, which shouldn't be there. This complicated integral term is some kind of memory term. So it describes some kind of covariance of the fluctuations, it will turn out. And then the final part is really the mean change of the system according to of the kind of reduced variables that I care about. So in some sense, the reason that the Mori-Zwanzig were so interested in this is it gives us some general fluctuation dissipation principle. And so lots of coarse-graining strategies essentially try to throw out these last two parts. And what we're going to ask is whether we can keep any information that's hiding in this complicated mess at the end here to improve our coarse-graining strategy. So as I said before I started the last slide, you might wonder, I mean, this was all done in terms of the linear system, right? So this L is, this is a completely linear equation that I started with here. So how on earth does that apply to the actual non-linear dynamics that I care about? Well, the answer is basically to think about how observables evolve, and then things become nice and linear suddenly. And this is a very cute technique in general. So basically, once you start thinking about the evolution of the observables, then it turns out that they obey certain linear PDEs, the Fokker-Planck equation, and that allows you to actually use all of this linear theory in order to study even nonlinear systems. It's just that you need to change your perspective slightly in order to do so. And so now to get into the meat of what this is really doing in this setting, so the projection P that I defined on the previous slide, really what it is here is a conditional expectation. So really we're doing this in an infinite dimensional space. So there's lots of details that, you know, you can take care of, but you need to be careful about in order to make sense of all of this. So the conditional expectation basically, you know, says, if I know only the value of the coarse-grained variables, then I can reduce any high-dimensional observable using only that knowledge. And so that is a very natural thing to do in lots of statistical, mechanical, and information theoretic applications, because this is kind of a very natural thing. If I only know about some part of my system, then if I know that there's some kind of probability measure lying behind everything, then if I take a conditional expectation with respect to that measure, that's kind of my best prediction for what is going on in that setting. Yes, so this turns out to be an orthogonal projection on L2 observables with respect to whatever measure we have underlying everything. And so the nice thing about all of this is that essentially by doing this projection using this P, then we can actually come up with a coarse-grained, closed coarse-grained variable and dynamics if we throw away the fluctuation dissipation terms that were in the Mori-Zwanzig formalism, it turns out. And so in some sense, by keeping those terms or trying to think about how to approximate those terms, we can think about how the error of any coarse-graining strategy based on this kind of framework can actually be measured and thought about. So that's in some sense what the point of what we're trying to do here is. Okay, so in the paper that we published on this, the first paper that we published on this, we basically prove the following theorem, which is just a kind of, I've already taken you through kind of the high level version of the proof, which is just to use this operator theory effectively. And then to do a little bit more work that comes from work done by other people, including Xingjie Li particularly, and lots of other people that have worked on Mori-Zwanzig before us, in order to write down these integral and fluctuating terms in a slightly different form. So here we were just writing this for this fluctuating term, and then the memory, it turns out you can write in this very particular way. And the PL, it turns out, can be turned into some kind of effective potential. So instead of this high dimensional complicated potential that's a function of V, we get an effective potential that's a function only of the coarse-grained variables we're interested in. And so that's all written here. This thing that's in here, we've again got the memory, we've got the effective potential inside this integral term, and we have something called a memory kernel, which is complicated because it's both a spatially dependent function that depends on the history and also the time that you can evaluate things at. So it's really not a pleasant thing at all to deal with in practice. And in some sense, I mean, all this is just a rewriting of the complicated dynamics into another, possibly more complicated form of the dynamics. So we haven't actually gained that much by doing this. But what we have gained is some insight into the structure of how to make good predictions and how to think about the dynamical properties of the system using this fluctuation and dissipation stuff. So in the particular case of the overdamped Langevin dynamics I introduced before, then the form looks like this. I think it's just the same thing that I wrote on the previous page. And as I've just said, these red and green terms here, sorry, not the last bit, but the red and green terms here are basically these additional Mori-Zwanzig terms. So people are already well aware of the fact that you can write down this term and this term to get an effective dynamics for a coarse-grained evolution. But then the additional terms that we gain here, if we can say something useful about those, then we can understand the error that's committed by propagating this effective dynamics versus taking the full dynamics and then coarse-graining. And so then if we take this as our closed model for some effective, for some reduced form of the dynamics, then we can understand maybe the error that we're committing. So yes, as I said, people have worked a lot on this already. So people like Tony and Fred have thought about constructing error estimates comparing the dynamics of these terms that I've written here with the dynamics if I evolved the full system and then took the observations that I would want to take anyway. And so what we wanted to do was see whether there's any additional information we can get from these leftover terms in this case. Yeah.
Can I maybe just have an overview of these terms here? So is it correct that the only stochastic fluctuation entering the system is coming from the Brownian motion, or?
So technically, there's also Brownian noise hidden in here as well. So this is also stochastic. Yeah.
And then, so but FT then so that noise won't be then Brownian anymore. I mean,
yeah, exactly. So that's exactly the point, in fact. So this M here is actually a covariance of the kind of this fluctuation thing, and so in general that won't be a Markovian fluctuation. It will have some time correlation, and so it will be nasty. And that's exactly the point. Like this is you can then start to think about what exactly is going on there. That's exactly what we're talking about.
Okay. No, no,
Is there anything else that anybody wants to ask at this point? Maybe just as we go.
Okay, no, so I mean, part of the reason why I asked is the FT, so probably some initial conditions entering there, but is there then also something really driving FT later on? You would have some.
So, yeah, I mean, to be fair, I mean, I think we're still in the process of understanding fully what this result means. So I think, yeah.
Yeah, okay, no, maybe we can talk.
Yeah. No, I'm happy to talk more, but yeah. No, exactly. I think there's still a lot to be understood exactly to unpick what this really means, because you can prove this theorem, but understanding what it really means is a different story, right? In some sense. So yeah, I think it's completely fair to ask this kind of question. And that's kind of going to be the punchline of the talk. I think we still need to do a lot of work to understand what's going on. But so what people do in practice is, so once you know that there is this structure that's hiding, you can try to, given that this is a data science seminar, I should probably try and say that there's some relevance to data science here. We can try to actually, if I take a high dimensional dynamical system and I want to actually come up with a surrogate model, then I would like to actually try to approximate these additional terms or throw them away, or, because every single term that's here on the right-hand side, including the S, the M, and this fluctuating force, I mean, all of them need to be basically described or parameterized in some way. And so that is where data science comes in, right, is to actually try to do this in practice for a particular example system. So there's a big problem there. And so the aim here was to understand, well, when do we actually need to approximate this M? We know that we need to approximate S because there's no other way to get an interesting closed system. So that's already known. But then when do we actually need to approximate M? How do we go about doing that? That's a good question. And then how is M connected to F here? And so, there's been a lot of research in the last 10 years into thinking about how we might fit these memory kernels. So what I've shown you is sometimes called a generalized Langevin equation, a GLE, because it's basically a more complicated version of the Langevin equation that I showed you before, with this time correlation in the noise now. And so people have done various work on thinking about when these fluctuations are very short-lived in terms of the correlation time. And so then you can have some kind of Markovian approximation, or if they're very long-lived, then maybe we have some other approximation techniques. And there's lots of literature on this, which I can send your way if you're interested. But the one thing that is quite common that Helen and I realized quite early on is that very often this the assumption that is made in these techniques is that this M is actually spatially invariant, which seems, based on some work that I've also done with some computational scientists, chemists, is definitely not true. So there's definitely spatial variation in even simple systems for the memory kernel, and this seems to play quite a significant role in trying to correct the dynamics. And so what we wanted to do was understand how that spatial variation interacts in things. And so we took this very simple potential that has quite a lot of interesting features and thought about that basically just to understand how the spatial variation plays a role. So the potential that we're going to take is just the potential given in terms of two coordinates, x1, x2. So it's not a very high dimensional example at all, but nevertheless, lots of interesting stuff will happen. So what we have is basically something that's quadratic in x1 here. So we have some parameter mu, which is basically giving us a kind of very shallow quadratic in the x1 direction. And then in the x2 direction, what we did was we're going to take a much steeper potential in the x2 direction, but then essentially move the kind of minimum in the x2 direction according to some sine wave, basically. So tau sine omega x1 is going to be the minimum in the x2 direction. So you've got a contour plot here on the right-hand side. And so you can see that basically the minimum moves along this sine wave. And so the thought here was, well, we want to explore something where the kind of pathway to get close to, so we know that the minimum of this potential is at x1, x2 equals 0. And that's the global equilibrium. And so in some sense, like the dynamics wants to generally tend, it's going to oscillate around because it's a stochastic dynamics, but it's going to want to be close to 0, 0. But now we have something interesting happening because actually we have a very complicated kind of structure to this potential because of the fact that there's a very low-lying, complicated pathway through the energy landscape where the dynamics generally wants to stay close to. And so in this case, we expect that actually coarse-graining this might give us some interesting results, and that's indeed what we're going to find out. And the motivation here is to think of something with an entropic type component here, right? So there's no energy barriers to getting close to equilibrium. If I think of a gradient flow, I can easily flow down and then along this pathway to 0, 0. But obviously the pathway I need to take is quite complicated. And if I reduce the system to just x1 only, then we'll see that actually I lose all of this information in this particular case. So I think this is fine because I've already talked about this at length. So we're going to choose x1 to be the particular coarse-grained variable we care about, right? So you can imagine that essentially if I think about x2 evolving, it's going to basically relax very quickly to equilibrium. So the thing where more interesting stuff is going to happen is in the x1 direction. And so that's what we might in general want to model, right? It's the more complicated dynamics, the longer timescale dynamics that we're interested in, often in these dynamical systems. And so essentially you can work through what all of these terms are. I won't go into too much detail, but I'll just highlight some of these things. So the first thing is that the effective potential in this case is really just this simple quadratic mu over 2x1 squared. And so if we discarded any of the memory effects, then we would see a very simple just minus the derivative of this plus Brownian noise for the effective dynamics. And what we'll see is that this really doesn't describe the dynamical behavior of the system very well at all. So the orthogonal dynamics you can work it out what it actually is in this case. And so it's complicated. And then essentially we can work through a kind of linearized analysis to look at the memory kernel in this case. Helen did some computational work here to actually show what happens to the memory kernel. So here you can see really that the memory kernel has a very significant spatial variation. So these curves on the right, these are all sampled curves based on dynamics. So there's quite a lot of computation going on here. So you've got the different curves on the left are at different time intervals. So there's some covariance type thing to evaluate what this memory kernel is. And you can see that the different curves are at different times. But the thing that's really clear is that the x1 variation of that memory kernel is very significant. Like it's orders of magnitude, a couple of orders of magnitude variation from one point to another. And so this really shows that the spatial variation of this memory is somehow significant and needs to be thought about further, at least in some cases, right? So this is a constructed example to show that this plays a role, but exactly when this is more or less relevant is important too. So yeah, the point is that the memory kernel in this case, because we've chosen a setting where we're taking a very significant timescale separation between x1 and x2, the memory kernel is going to decay very fast. That has a very significant spatial variation. That's the point of this, essentially. And so it suggests that we need to take some of that into account if we want to propose an effective dynamics that's better. So the way we did that is kind of ad hoc in our results. So we basically linearized around this kind of slow manifold that we've constructed and look at the relaxation and do some asymptotic analysis. And if you do that, then you can come up with an approximation for how the orthogonal dynamics behaves, at least in the mean. And so then, I mean, I'll spare you the details, but in short, we can come up with an approximation for the terms in our effective dynamics based on basically using Laplace's method for these exponential integrals. So assume that this linearization is a reasonable approximation, then use the fact that we have an e to the minus lambda times something complicated, and then do kind of a classical asymptotic analysis to turn those exponential integrals into something which is just an evaluation. And in this case, you can write down what that is, and you get some dynamics which looks like this in the end. And as I said before, I mean, fully understanding how this works in general, I don't yet understand, and I would like to. So if anyone has any ideas about that, it would be great to talk about it. But so what we do end up with is essentially a new effective dynamics that takes into account this memory effect, and seems to have something to do, right, because of the presence of these tau squared, omega squared, cos squared, omega x terms, to do with the fact that there is some manifold, slow manifold, and how it changes in the x1 direction. So, yeah.
Yeah, maybe. So, can you interpret the drift term here as the gradient of potential in this case? Probably not. No, not.
Well, so because it's 1D, I mean, you can always write down a potential, okay, right? But so whether in general that's true, I'm not sure. And so, yeah, this is another thing, right? This is a very special thing because we're only working in 1D. So we should really do a higher dimensional example to understand exactly the structure of this term in general.
Yeah. No, because I think, okay, if you have the Brownian motion with a noise which depends on the position, I guess you have usually typically like an additional. So yeah, okay, no, sorry. Yes.
What is the invariance?
Sorry?
Invariant.
So, well, I was going to come to that in just a second. So it turns out, well, let's actually skip to that, right? Because you've just asked about it. So it turns out in this setting that because there's a square root of this term and a version of that term, it has the right invariant measure. So that's another slightly mysterious thing to me that somehow we managed to stumble upon. Well, obviously it's not a coincidence. There's something more interesting going on, right? So it has the correct invariant measure for the coarse-graining dynamics, actually. Yeah. So if you do something more naive, which is the other thing that we explored, which is just taking like some more simple covariance, like you might actually do in practice if you had a high dimensional thing, like really just compute basically one step of this orthogonal dynamics, this fluctuating dynamics, and then compute the covariance, then you get something completely wrong. So there's something else.
This is not the one that we got, right? This is not the previous one.
This one is the one that we came up with. And this one is a more naive approach, which I mean is clearly wrong, because it doesn't have the correct invariant measure anymore. In fact, it will go completely wrong. We'll see in the numerical results. So let me actually show you that next. So first of all, we just looked at just simulating what happens if we take put no stochastic noise in. And so we've got various options for the dynamics here. So the red is the full system that's coarse-grained. So the red thing you can see here, this is a cutout. The green is basically on top of the red. Green is going to be our nice choice of dynamics. That's a spoiler alert. The blue one is where we don't take any memory effects into account, and the pink one is our naive approximation that just converges to completely the wrong equilibrium. So that's completely wrong. The blue will have the correct invariant measure, as we've discussed just now, and the green also has the correct invariant measure and also seems to capture the dynamical properties of the system way better, right? And this is just hugely better in this particular setup that we've got here. If we reduce the oscillations of the so if we kind of flatten out this variation in this complicated path, then like everything gets much better for the simpler dynamics, because essentially the memory effects just reduce because it's, you know, the oscillations are only a small perturbation, and so in this case they're all fairly close together, and that's what the right hand picture is. So that's no thermostat, so no temperature, and so no stochastic noise. We can also do the same thing for stochastic noise, and essentially we see that we are getting it pretty much right. The higher that you take the temperature, the worse things get, but that's also harder to sample, but you still see that we're getting pretty much a good prediction of how things should go. So that's nice to see. So we do seem to be capturing some dynamical information here that is lost if we just take the effective potential alone. So let's just skip all of this to here. So observation is this seems to work in this particular case. So that's good, of course, but it's been constructed in such a way such that it kind of works. So what we would like to do is understand, in general, when do we need these memory corrections? When do we not need these memory corrections? Because it's very expensive to actually evaluate them in practice. Or maybe is there a simple way, a relatively cheap way to evaluate them in practice and work out when they are needed? And it seems that these memory effects do capture some of this nature of. It seems to suggest that the memory effects capture some of this entropic barrier behavior, right? It basically tells us more about how the dynamics is impeded in a coarse-graining variable by taking into account some dynamical behavior that is not present in effective potentials in general. And of course, the question is, you know, is this really realistic or relevant to people in practice? The answer is, I'm not sure, but I think that there are definite examples of cases where entropic barriers are significant, and maybe if we can turn this into something usable, this could be relevant for those people. So let me just kind of come to a conclusion here, and then maybe I can take some more questions. So we have used this Mori-Zwanzig framework to derive an effective equation for linear reaction coordinates in a simplified dynamics over Langevin dynamics. So yeah, but we believe that we can basically take this further and do something similar for other kinds of dynamics. But there's still a lot to be understood, I think, here in terms of really working out what happens in a general setting where we have some kind of reduced manifold, which is a very common setting that people, you know, believe that there are reduced. There's a collection of degrees of freedom that really are the main ones that we care about in lots of these systems, and so we'd like to understand in greater generality, if we have some kind of manifold like this, how does that interact with coarse graining, and understand when we need to think about that more carefully and when it might be relevant to the coarse-graining dynamics. And so what are we doing at the moment? So we, in order to push this a little bit further, we're just in the process of finishing up a preprint on the complete story in just a really simple linear dynamical system setting, which then we hope to use to basically think about the fact that we used a linearization around a slow manifold in this high dimensional setting, and that will hopefully give us all the pieces to go to more complicated dynamics. And that's basically the latter 2 points. Yeah, I think there's other applications to other more complicated two-scale stochastic systems, so that's something that's quite common to look at. It's a very classical kind of multi-scale mechanics, multi-scale problem that people have thought about, and I think that something about what we've done seems to go slightly beyond the kind of classical stochastic averaging stuff here, based on what I've talked to people about. And so we'd like to understand really the interaction between what we're doing here and classical stochastic averaging, and whether we're saying anything more. So just to wrap up, yeah, I'd like to say thanks to Helen, my collaborator on all of this work. And we were both funded through various things that I've listed here. And so thanks to for funding, and thank you for listening.
Thank you very much, Tom, for the very interesting talk. So do we have any questions online? If you do have any questions online, please just unmute yourself. Or if you prefer, you can just type in the chat box. So if not, do we have any questions in the audience? Hong?
I have two questions. So can you define do you need scale separation?
So, I mean, in order to write down the theorem that I wrote down, there's no requirement to scale separation. I think I'm still on. Okay, you muted me. Okay, fine. So the question was, do you need two-scale separation? So in order to do all of this particular example, yes, you need the scale separation. So the time scale separation clearly is playing some kind of role in terms of determining when this entropic effects seem to be more important in this Langevin setting. But in order to write down the theorem, I mean, you don't need to, because it's just, you can apply whatever you like, any mapping you like, and still write this theorem down. It's just whether you can then interpret anything out of the theorem in some sense. So the kind of scale separation is the classical setting for where you try and do a Markovian approximation, right? That's essentially what we got. You can go beyond that and try and do something where you take a more complicated autocorrelation for your noise and things like that. But yeah.
Second question, in the full Langevin case, what would affect the reaction coordinate? What do you think of it?
So I think basically, I mean, this is a complete guess because the calculation is not completely trivial to do these things, and we haven't looked in real detail at the full Langevin case. So what I think is, again, you'll get basically, what you'll get is that you'll get a gamma in your Langevin equation, which is dependent upon space, basically. So you'll have a gamma of Q, or whatever your reduced variable is, and that will have some complicated relationship to the geometry that I believe exists here that I still don't understand. So
can I just jump in here? So in the full Langevin case, how difficult is that, like, to reproduce your calculations in this paper?
So I don't know, because I haven't tried in any detail. But yeah, we should, basically. I mean, it's one of these many to-do things on the to-do list, but I can't say I've tried. But yeah, maybe it could be straightforward, actually. But yeah.
So we did look on coarse-graining of full Langevin, but in the sense of level, we do not take the memory term. For the full Langevin, we can work with non-linear in Q, but linear in P.
Okay. Yeah. So I mean, I think that there's kind of a classical. So the people that do MD, like do this properly for MD, they always use canonical transformations, which is probably the right thing to do. So you define some averaging on your Q, and then you define kind of a conjugate momentum, which is the right way to average in P, because otherwise you're going to get something that doesn't preserve all the nice structure that you have. So, again, I think there's lots that can be done here, but yeah, I haven't done it. So, yeah.
Yes. Oh, okay. Sorry. Thank you for the very nice talk. So just like for the bigger picture, so if I understand you correctly, so you're mainly applying the Mori-Zwanzig formalism here in order to get the reduced dynamic, which preserves then actually your target or the measure, marginal measure, and the variables, or like the collective variable you're interested in sampling. But have you also looked about like the approximation then of the path measure?
So that's
For the dynamic?
that was kind of the motivation, right? Because the point is that, I mean, in practice, like if you want fast equilibration to sample your measure very effectively,
Yeah,
the
okay.
blue is what you want.
Um,
Right. So whereas the green it's giving you more dynamical information. So that's exactly yeah. So the aim was really to think about how the path measure behaves, and like yeah, we've started some work with I guess you guys don't know, with Panchu and Panchu Sharma and Bastian Hilda to actually think about the proving some, because Helen and I are not really proper stochastic analysts, I should say. So we're talking to them about doing some more precise estimates. So I know that Panchu's worked on the kind of Lagolier estimates and trying to understand whether we can actually prove some probabilistic path measure estimates in this case. But yeah, that's just started. So.
Okay, and because otherwise my follow-up question would have been like, where you see the advantage. I mean, if you're just interested in something, the stationary measure, whether there would be any advantage of doing it this way, where you have kind of like dynamics, which might be not like, I mean, not a standard Brownian dynamics you end up with, in the sense like you have the position dependent somehow diffusion term, and then yeah, you have the E2 correction. Whether there's any advantage of doing it this way over like just trying to find the free energy.
So I don't think like for my view would be like for any equilibrium quantity, I mean, we're not gaining anything, like any like static equilibrium quantity. But so for diffusion coefficients, you do care about this kind of thing, right? So the thing I didn't talk about right at the very start, maybe actually it's quicker for me to do this. So in MD, a classical thing that people care about is like motion through, so this is a biological two-phase co-block polymer, and you care about kind of how often does this green migrate through here, and that's really a completely dynamical quantity that has no static like analogy, and so that's really what we were interested in, because that's kind of the entropic barrier setting that people care about in some areas of particularly biological MD. And so that's really something where you don't have any energetic barrier so much as just like the green has to just find its way through here somehow. And so that's a timescale problem that you care about. And so then the dynamics, getting the dynamics right is important. And so, yeah, but in some cases, yeah, having the wrong dynamics is advantageous for exactly the reason that you say.